In the video for exercise 28a, we developed this sort of schematic for how you can turn a ketone into an acetal. So our ketone in this example is going to be this cyclobutanone, and the acetal that they're giving us has two ethoxy groups in the place of the ketone. And we saw in A how you make this transformation from a ketone to an acetal, and an acetal is a compound that has a carbon with two ethers on it. So you make that transformation by adding excess alcohol. Okay, well, halfway there, you turn the carbonyl into an alcohol, and you put one of the two ethers onto your carbon chain. That halfway point is called the hemiacetal. And so here is a picture of our ketone in this specific exercise, our acetal that they gave us, and the hemiacetal in between. So you put one of the ethoxy groups on, one of the OR groups on, and the other is an OH that's ultimately coming from the oxygen in the ketone. And we saw how there are several steps for this. To go from the ketone to the hemiacetal, it's a process that's bookended by proton transfers. Sandwiched in the middle is a nucleophilic attack. To go from the hemiacetal to the acetal, again, a process that's bookended by proton transfers. In the middle, first there's loss of this leaving group, and then nucleophilic attack to put the second ethoxy group on. So we went through the reasoning behind all of those steps in that previous video, and in this one we're just going to walk through and see them applied to a different molecule. So we have our ketone to begin with, and the carbonyl carbon in this is a good electrophile, but we need to make it an amazing electrophile, because our nucleophile, ethanol, which is drinking alcohol, is very stable. It has no full charge on it. So that's a very weak nucleophile, ethanol, and so to get it to react with this in a way that is efficient, we want to turn our electrophile, our carbonyl carbon, into an amazing electrophile. And we do that with a proton transfer. So you'll have this cyclobutanone, and we're going to treat that with an acid. Now the acid they give us in this happens to be toluene sulfonic acid. I can show you what it looks like. It's almost like sulfuric acid. Sulfuric acid is just putting a hydrogen on each of these ends, but on one of them you have a toluene group, so like a benzene ring with a methyl group on it. And you can see why this is a good acid. This hydrogen here can leave, and the electrons that are left, because the electrons that are left behind and the negative charge they have are stabilized through resonance. They're allylic to both of these pi bonds. And because one of these lone pairs can exist in a p orbital, they can even spread out over this entire molecule. So you can see why it's a strong acid. Now you don't need to be able to draw that, because when you put a strong acid like that into water, it gives all of its H's away, and the acid that we're actually going to be dealing with is hydronium. So to get this first proton transfer step done, we're going to use hydronium. The slightly negative oxygen in the ketone steals one of the slightly positive hydrogens in this hydronium ion. The hydrogen can only form one bond, so the electrons in the bond that are already there ricochet back onto the most electronegative place nearby, and that's that oxygen there. And they go to stabilize that positive charge. So that's our proton transfer. Now after that first step, we're left with a structure that looks like this. So now we've turned this what was a good electrophile into an amazing electrophile. The carbonyl carbon was slightly positive before, but now the oxygen, in addition to being very electronegative, has a positive charge that's pulling electrons towards it. And so the electrophile we have is very, very, very slightly positive, almost a full positive charge. And we discussed in terms of resonance how you could reframe your thinking about that in the previous exercise. So the electronegative oxygen here acts as a nucleophile, swoops in, and attacks the carbonyl carbon. The pi electrons, the pi bond is the weaker bond, the pi electrons break, and they go on to the more electronegative place nearby. So that's our nucleophilic attack. So after that step, we are left with an OH, and on the same carbon, we have our ethanol molecule. Still has the H and the 2 carbons. Now it has a full positive charge. So to stabilize that, we have to do a proton transfer. And we can do the proton transfer with the water that we made. This hydronium ended up making a water molecule. Because it influences the story of this carbon chain, we'll draw it again here. That water molecule, the slightly negative oxygen there, can steal the slightly positive hydrogen. The electrons go on to the oxygen nearby. And that gives us our hemiacetal. So we're halfway there. We're halfway to the acetal. We've added one of our OR groups, one of our alkoxy groups, in this case an F-oxy group. But we still have an OH. We need to make that leave. So remember, a hemiacetal is a compound that has a carbon that with an ether and an alcohol bonded to the same carbon. So we need to make this OH leave, but it's a bad leaving group. So we'll do a proton transfer to turn it into a better leaving group. And the acid that we're going to use to do that is going to be hydronium. So this OH, slightly negative oxygen, steals the slightly positive hydrogen on this hydronium, and the electrons go onto the most electronegative place nearby. So that's our proton transfer. The molecule we get at the end of that this oxygen is now going to have 2 hydrogens on it, and just 1 lone pair. That gives it a full positive charge. Now that's an amazing leaving group. It's an amazing leaving group, and it can leave. So we can have loss of a leaving group now, because if this, basically water, takes these electrons and goes, it ends up as a very stable molecule. Now it's not just going to take those electrons, it needs a little push, and this whole time, this carbon here, that used to be the carbonyl carbon, is really slightly positive. It's bonded to 2 oxygens. The whole time, these lone pairs have been wanting to form a new bond there. They've been attracted to the slight positive charge. But so has this molecule, so it stays on. Well now, when these electrons push to make their new bond, this is such a good leaving group that it gets kicked off the molecule, and you end up forming this molecule here. So we have loss of a leaving group in that previous step. Now if you'll notice, this molecule is very similar to the molecule we had after the very first protonation step. The only difference is that instead of the hydrogen, it's an R group. But what we have here is an amazing electrophile. The carbonyl carbon is slightly positive because it's bonded to oxygen twice, but the oxygen has a full positive charge. That means that it's pulling electrons to itself even more intensely. And so this electrophile is losing those electrons and becoming even more slightly positive. So we have another nucleophile attack. Now remember, we're treating this with excess alcohol. And our nucleophile is ethanol. It's a poor nucleophile, it's a weak nucleophile. It's slightly negative, but no full charges. Nonetheless, we have such a strong electrophile that the nucleophile is able to attack. The pi bond, the weakest bond, breaks. The electrons go to the oxygen to stabilize it. That's our nucleophilic attack. And we're left with the ethoxy group that's already there, stays there. Now it's only a single bond going to it. And now we have this other ethanol molecule attached. Well, this oxygen has a full positive charge. And so that's unstable, so we just have to do our last step, the proton transfer. So we need some sort of a base to take that H+, and we can use the water that we made in a previous step. This water that acted as a leaving group was formed over here. That water can swoop back in, jostle around, and the slightly negative oxygen steals that hydrogen there. The electrons go onto the electronegative oxygen, and we're left with our beautiful acetal. Now the way they're writing this in the exercise as the answer is like this, but notice this is the same exact thing. The ETs stand for ethyl groups, and that's what we have here. So this is the same molecule. And that is our acetal. We have two ethers, an oxygen with a carbon on both sides, two ethers bonded to the same carbon. So we've shown how you can get an acetal using those same steps that we built up in part A for this, using these same 7 steps. So as an overview, quick overview, we do a proton transfer in the beginning to turn the carbonyl into an amazing electrophile. Now it will react even with a weak nucleophile like an alcohol, so we can do nucleophilic attack. Once you have that group on there, the ethanol molecule, the alcohol, has a full positive charge, so we did proton transfer to stabilize it. That gave us our hemiacetal. To get the full acetal, we need the OH to leave, so we turn it into a better leaving group through proton transfer. It gets kicked off by the lone pair on the OR group, in this case the ethoxy group that's already there. So we have loss of a leaving group. That gives us an amazing electrophile again. That will even allow a weak nucleophile like another ethanol molecule to attack. Once it attacks, it has a positive charge, and we neutralize that with a proton transfer by taking the H+ off. And that gives us our acetal. Okay, well, with C, it's really the same thing. The only difference, it's the same process, the only difference is the carbon chain. So the ketone that we're dealing with is going to be this ketone here. It's 3-methyl-2-butanone. That's our ketone, and then we're going to add excess ethanol, so excess drinking alcohol. And ultimately, what we get is an acetal where the ethanol molecules, 2 of them, replace the 2 bonds to the carbonyl oxygen. So that's our full acetal. That's the overall process. Now the halfway point is where we've only added 1 of the alcohols. The other oxygen, the carbonyl oxygen, stays there as an alcohol. Oops. So let's draw this. We have this methyl group. We'll have 1 of our alcohols. Otherwise, we just have the OH. I say alcohols. Once it's on the molecule, it's an ether, but it was added as an alcohol. So that's our hemiacetal. We've put on 1 of the ethoxy groups. The other one still has to be made. So we're halfway there. It's half the acetal and half the original ketone. It's the hemiacetal. So this is our overall process. We're going to follow the same 7 steps. Remember, going from the ketone to the hemiacetal, proton transfers. That process is bookended by proton transfers. Going from the hemiacetal to the acetal, the process is bookended by proton transfers. Because we're adding an ethoxy group onto this, we have to do a nucleophilic attack in the first half. In the second half, because we're removing the OH and adding a second OR group, we have to do loss of a leaving group and nucleophilic attack in the middle. So those are our steps. Let's look at them in detail. The first thing we want to do is to turn the carbonyl carbon into an even better electrophile, because our nucleophile ethanol is very stable. Ethanol is not a very reactive molecule by itself. It doesn't have a full charge. So to get it to react as a nucleophile, slightly negative, but to get it to react as a nucleophile, we need to make our electrophile even more electrophilic, even stronger. And we can do that with a proton transfer. Now, we want to add an H+ onto this molecule, so we're going to add an acid. And you can see here they're giving us catalytic sulfuric acid. The brackets mean that it's just acting as a catalyst. You don't have to draw sulfuric acid. We have water in this beaker. When you pour sulfuric acid into water, the sulfuric acid gives away all of its H's, and the effective acid that you have in solution is hydronium. So that's the acid that we're going to use. So we have hydronium. Our slightly negative oxygen on the carbonyl can act as a nucleophile and attack one of the slightly positive hydrogens. All of the hydrogens are slightly positive. It doesn't matter which one you take. So that attacks that hydrogen. The electrons go to the oxygen to stabilize the positive charge there. So that's proton transfer. Now, after that step, we have this first amazing electrophile. And this is an amazing electrophile because the oxygen is not just really electronegative. Now it has a full positive charge to lure electrons to itself. And so the carbon it's bonded to is losing a lot of electron density. It's really slightly positive. And we also had a water that we made here from that hydronium that lost the hydrogen, or the H+. So now that we did a proton transfer to turn our good electrophile into an amazing electrophile, we can have our weak nucleophile attack it. It attacks the carbonyl carbon, the pi bond breaks, the electrons go to the most electronegative place nearby. So that's our nucleophilic attack. So after that step, we will have an OH here with just a single bond connecting it to the carbon chain. Also coming off of that carbon will be our ethanol molecule, so the 2 carbons and a hydrogen. That oxygen has 3 bonds, so it has a positive charge. So we're almost at the hemiacetal, but this molecule here has a positive charge, so we need to stabilize that. We can do that with a proton transfer. We can take the water that we made, and that can come back and act as a base. The slightly negative oxygen in the water can steal the hydrogen, the slightly positive hydrogen here, and the electrons can snap onto the oxygen to stabilize the positive charge. And that gives us our hemiacetal. So this is a hemiacetal because we have a carbon that's bonded to an ether on one side and an alcohol on the other. So it's an ether and an alcohol on the same carbon. That's a hemiacetal. All right, we're halfway there. So after we have this hemiacetal, we can do a proton transfer to make this leaving group a better leaving group. Right? We have 2 things. We need to get that leaving group gone, and we need another ethanol molecule to attack. So we have to do loss of a leaving group and nucleophilic attack. But in order to get this leaving group to leave, it has to turn into a better leaving group. We can do that by taking this acid that we formed in this last step. So now we have this hydronium. The slightly negative oxygen of the alcohol can attack one of the slightly positive hydrogens. Those, excuse me, those electrons can go onto the oxygen to stabilize the positive charge there. And that turns our bad hydroxide leaving group into an awesome water leaving group. So here the leaving group was OH. That's very unstable if it takes electrons and tries to leave the molecule. But here we have water. If it takes electrons and tries to leave the molecule, it's water, which is very stable. So now that we have this amazing leaving group, the leaving group can leave. Now it needs a small push. This carbon here that's bonded to two oxygens is slightly positive. The electrons on the oxygens have both been attracted to that. That's part of what keeps the oxygens there. They keep trying to push and create a new bond there, but the other one pushes it away. Well, now that the leaving group is a good enough leaving group, when this lone pair on the ethoxide tries to form a pi bond, it kicks the leaving group off, and we get loss of a leaving group. So now we have this molecule, and we also have water. This turns into water, and what's left is this molecule here. Notice the similarity between that molecule and what we had toward the beginning. It's the same thing, it's just an R group is replacing that H. And just like this was an amazing electrophile, so likewise we have an amazing electrophile now, because not only is the carbonyl carbon losing electron density to the oxygen because it's electronegative, but the oxygen has a full positive charge that's sucking the electrons away from the carbonyl carbon. So this is a really, really vulnerable electrophile. So you can even take a weak nucleophile like another ethanol. Remember, we use excess of the alcohol. Another ethanol molecule that can come in, swoop in, attack that carbonyl carbon. The pi electrons go to the most electronegative place nearby, that's the oxygen. There's our nucleophilic attack. And we're left with this OR group and a full ethanol molecule. Now that oxygen there has a positive charge because it has 3 bonds. So we're almost there. We almost have the acetal. We just need to get rid of that positive charge. And we can get rid of it by taking this water that we formed in the previous step and use it as a base. The slightly negative oxygen can steal that slightly positive hydrogen. The electrons can snap back onto the oxygen to stabilize its full positive charge. You see that that's a proton transfer happening. And once that's done, you'd have your acetal. So the way they draw this in the exercise above is OET, but notice those ethyl groups, those ETs, it's just a CH3CH2. So those are the same thing. And that is our beautiful acetal. We have 2 ethers bonded to the same carbon. Okay, so hopefully this helped a little bit, at least seeing how the mechanism that we built in exercise 1, once you understand all of those steps, how you can start to apply them to different carbon chains and different alcohols.